So how do we work out this correlation coefficient? We need to come up with a way of doing it. Visually, the line of best fit, fantastic, but how do we come up with that number of correlation? So this is what's called the Pearsons correlation coefficient. The symbol is R if you're talking about a sample, rho if it's a population. There's the formula. Of course, there's a new term in there that we don't know yet. So the correlation coefficient is equal to the covariance of x and y over the standard deviation of the x's and the standard deviation of the y's. Now, you'll recall that when we worked out variance, it was the expected value of x minus the average squared. That's where it came from. Covariance then, instead of going x minus the average squared, we just look at each individual bit of data. We go x minus its average times it by y minus its average. The simpler way of doing that for covariance then is to do that. We find the average of x and y multiplied together, and then we subtract the averages multiplied together. The answer should end up between -1 and 1. If the correlation is 1, that's perfect correlation. In between 0.6 and 1, we say, okay, it's a strong correlation. In between 0.4 and 0.6, moderate correlation. 0.1 and 0.4, weak. In between 0 and 0.1, virtually no correlation. And of course, if it does turn out to be 0, well, then there's certainly no correlation whatsoever. Positive means they move in the same direction. As one goes up, the other goes up. Negative would mean they go in opposite directions. Let's do this example. The birth weights, and then they went back 21 years later to those same people that they weighed at birth and see, let's tell you how much they weigh at age 21. And so there they are. First thing we're going to do is draw a scatter plot and see exactly what it looks like. There's our scatter plot. So I've put birth weight on the horizontal axis and age 21 on the vertical axis. So it looks like, just visually looking at that, it certainly looks linear. And I'd say it looks like it's a strong linear correlation. Just visually looking at it though is not really good enough. We want to come up with that number. So we'll calculate it. Okay, X is going to represent the birth weight. Y is going to represent the weight at 21. So there's those values we just saw. Now, all the bits of information we need to do this. We need the sum of each of those. Okay, X times Y is going to come in handy. So we'll multiply X with Y and there's our answers. Well, if we're going to work out variance, we're going to need X squared and Y squared. So I've worked out each of those. Okay, average will be the sum of the X divided by the frequency. Well, there was 8 pieces of data. So there's my average for X. And I can do the same with the Y's. There's my average for Y. I can now average the X times Y. We needed that in our formula as well. Now we can work out the variance of the X's, and then the square root of that will give me the standard deviation of the X's. Then I can do the same with the Y's. I think we now have all the information we need to sub into that formula. So the correlation coefficient turns out to be 0.7862. And that did fall into our category of strong. How do we actually come up with the equation of the line? So rather than doing it by the line of best fit, we actually find the actual equation of the best possible line of best fit, if you like. And it's called the least squares regression line. So we're going to find it. Now what this does, obviously we have to assume that they are linearly related. It works great when you don't have outliers. Outliers always cause problems. And what it tries to do is, when you draw a line of best fit, obviously not all the data is going to lie on the line. There'll be some above it, there'll be some below it. So what this is trying to do is minimize the sum of the squares of the vertical distances from the line of best fit and the dot. Now why squares? Well, because some will be below and some will be above, so some's negative, some's positive. Square it, you get a positive number. The other thing we want to do with this line that we're creating, we want to make sure it goes through the average of both the X and the Y. That becomes a point on the line, the average of X with the average of Y. The slope turns out to be this. The covariance of XY over the variance of X. If we use our formula then to make it a bit neater, It'll be average of xy minus average of x times the average of y divided by the variance, so that's s squared for variance. But we can do better than that, because what I've got on top is actually the correlation coefficient times the standard deviation of x times the standard deviation of y, which cancels with the denominator, and we come up with this neater formula to find the slope of the line. Correlation coefficient times the standard deviation of the y values over the standard deviation of the x values. How to remember which one's on top, which one's on bottom? It's coordinate geometry. The y's go on top, the x goes on bottom when we're talking about slope. Difference in y's over difference in x. Okay, where's the y-intercept? Well, that's going to be the equation of our line, because remember we said it has to go through the point x average, y average. So we can use that to create the y-intercept. It'll be the y average minus the slope that we just worked out times the x average. Okay, let's now go back to our graph. I'm going to draw a line of best fit. And I promise you, I did this before coming up with the equation, okay? So that was the one I came up with for the line of best fit. Now, 2 points that are on that line are 250. If you'll notice, it goes through the point 250, and point 27540 goes through that point there. That's basically, well, for want of a better word, the x-axis is hitting. So I can work out the slope of that line. The slope of that line is 5.7971. So y minus 50 will equal 5.7971 x minus 2. Point slope formula. That's what I reckon the equation of the line of best fit is. How good did I go? Let's find the actual one. Okay, using our formula, there's the slope of the line. And I can now work out the y-intercept, 39.616. That's the actual best line of best fit, if you like. Draw it on there. Well, points that I know it goes through. I know it goes through those 2 points. That wasn't too bad. That's pretty good doing it by eye, I thought. A cricket, by the way, is an insect. Well, thanks for that. The male cricket produces a chirping sound. A scientist wishes to explore the relationship between temperature and the number of cricket chirps. And this is what scientists do. They probably get paid a fortune, some government grant, and they work out this useful information. So once a day for 20 days, the scientist collects the data, and there's the box plot of the data. The other thing we know is the average temperature was 0.525 degrees Celsius below the median temperature. And a third piece of information, they managed to count 684 chirps when they collected their 20 data points. So that was the information they were given. A bit more information. They actually told them the equation. They didn't have to work it out. So they actually told them the equation of the regression line. And then they reminded them that, oh, by the way, the line will always go through that particular point. And in case they didn't realise what x bar, y bar was, they even reminded them that x bar is the average of the temperature and y bar is the average of the chirps. Okay, we're almost at the actual question. Calculate the number of chirps expected in a 15-second interval when the temperature is 19 degrees. That was the question. There was no lead into, like, as in here's part I, part B. From memory, it was a 4 or 5 mark question. So there's a bit of work to be done. So they had to get all that information and work out the number of chirps in a 15-second interval when the temperature is 19 degrees Celsius. Well, let's work out the average. Remember, they told us it was 0.525 below the median. Well, we could look at that box and whisker. We can see where the median is. Subtract 0.525, we now know the average of x. It's 21.475. The average of y, they collected 684 chirps. Divided by 20, it was over 20 days. So on average, there was 34.2 chirps. We now know x bar and y bar. We know the regression line, and just in case we forgot, they told us it goes through x bar, y bar. So we now know a point on the regression line. Well, hang on, if we know a point and they've given us the equation, we can sub that point in and work out b. So we sub that in and we work out b is, well, yeah, you can see I didn't bother working out what it actually was. I left it as 44.8063 over 21.475, whatever that is, because all I'm now interested in is what is y when x is 19, because x represented the temperature. So I just plug that in, 29.03, well, we'd be expecting 29 chirps. There you go. 15A, I think the book has a slightly different formula. Use our formula that we put in the theory there. I think it's easier.